phase chemical dynamics group. I'm going to tell you a little bit about what we do, but not so much in detail, but just sort of to give an overall picture and then sort of show sort of what our strengths are and a little bit of what our weaknesses are and how you might help us. So to go on, let's first start out with the motivation. So I'm going to talk about combustion. Currently, about 85% of our nation's energy supply has its origins in combustion. And while that may change and go down significantly, it's not going to go to zero anytime soon. And it's probably going to stay substantial for a fair amount of time. And in particular, in the transportation sector, the combustion of either conventional or alternative fuels is likely to be quite important, particularly in jets and things like that. And so basically, our group is funded by the Office of Basic Energy Sciences, and their belief is that we'll be in a much better position to achieve our energy conservation and environmental goals if we had accurate and reliable ways to predict the performance of combustion devices. And so our goal is really to go from, this simple or elementary idea of combustion in the pavement to these more advanced ideas of high-performance automobiles by using modeling as opposed to the traditional sort of Edisonian approach. So our group at Argonne is really focused on aspects of combustion chemistry and looking at sort of trying to understand that both from experimental and theoretical perspective. We have a group of about 10 staff members with a 50-50 blend of experiment and theory. And we're really sort of reasonably vertically integrated in these areas where we have experimental and theoretical thermochemistry. We have people developing and using electronic structure methods. We have both theoretical and experimental studies of chemical kinetics and chemical dynamics. And most of these are focused on elementary reaction kinetics and their pressure and temperature dependencies, although we do have some work as well on coupled chemical kinetics, that is putting together multiple reactions in a much more complex environment and trying to understand what's going on. These all contribute from the chemistry perspective into our goal of developing accurate predictive models. Of course, we're not considering, for the most part, fluid dynamics or the transport that's also important in modeling combustion devices. And that's an area that we want to grow into and where people at Northwestern might contribute. Now, our group is really focused on the combustion chemistry. And from our perspective, this is really sort of a nice thing. Many people believe that we're sort of entering a golden age of kinetics for this idea of elementary rate constants, where theory can really be used to generate accurate and reliable comprehensive rate constants for use in models. And this would include the temperature and pressure dependence of the reactions. Our group does electronic structure calculations. We generate chemically accurate potential energy surfaces and calculate rate constants that can be used then in chemical models. And on the left-hand side is just some examples from the work that pretty pictures. It's important, again, to be able to calculate these things because in a typical chemical mechanism for burning like a typical hydrocarbon fuel or a biofuel, there's typically hundreds of species that are involved in thousands of chemical reactions, and you're interested in using those in a range of temperatures and pressures, and so you need the rate constants over large ranges of conditions. And in this case, getting all those values and behavior experimentally is really quite difficult, but if we can do it theoretically, that's great. In reality, at the moment, we feel really good about certain kinds of reactions and can predict them very accurately. In reality, that there still are kinds of reactions that are very difficult to calculate accurately. And so we are still in the process of developing ways to treat those kinds of reactions, as well as using experiments to get more insight into those reactions. But that's actually something that our group is sort of working on, and while we've collaborated with people at Northwestern in the past, in particular George Schatz, that this is something where we're reasonably comfortable. So to just talk a little bit about argon strengths again, so we have this idea of the electronic structure, and using those methods, generating the potential surfaces and getting the rate constants, as well as the thermochemistry that's involved in all of these things. And in hydrocarbon combustion, one has a lot of thermochemistry of radicals and other reactive species that's difficult to get sort of using traditional methods. Another strength at Argonne, which is not in my group, but in another division in the energy systems division, that they actually have quite a large group that's devoted to studies of engines and emissions, that is using real engines, test engines, and doing experiments. In that group, they do work using X-ray imaging of fuel spray dynamics, and Jin Wang is here from the Advanced Photon Source, who is also sort of the guy in charge of that kind of work. They also have rapid compression machines, which are sort of a simplified way of studying chemistry and reaction dynamics under sort of very controlled conditions that mimic the conditions in an engine cylinder, as well as real engines and real test facilities where they can run different engines on different fuels and see what happens. But and what we're trying to do at Argonne to some extent is to try and tie these two groups together. We have sort of the fundamental side and the chemistry, and we have the sort of very applied side with the engines and the fuel studies. But what we really need to do is to connect those two things together more. We're working on that at Argonne, but this is again an area where Northwestern might help. So our weakness sort of lies in the idea of connecting these two things together, and where we feel, I mean, the way to do this is through combustion modeling. And so what we need, and so we sort of view this as sort of being three levels of combustion modeling that can be important. One is simply the chemical modeling of the complex reaction mechanisms, that is looking at just the chemistry alone and considering very, well-stirred, well-mixed situations. Second, in more realistic considerations, one has to include transport phenomena and include the mixing of the transport phenomena as well as the chemistry and model those things together. And finally, device modeling, wherein one models actually the specific conditions of the instrument or the device that one's interested in. At the present time, although both of our groups do a little bit of these things, our group does a little bit of chemical modeling. For the most part, the output of our group goes to chemical modelers at other institutions, such as at Livermore or at Sandia and other places like that. Similarly, the engines and emissions group, while they do a little bit of modeling, they tend to get their modeling expertise by collaborating with people like at the Engine Research Center at University of Wisconsin or at Sandia or at other places. And we're trying to incorporate these into our groups at Argonne as well. And so this sort of gives sort of a basic overview of sort of where we're trying to go. And sort of we have really strong fundamental chemistry, and we have strong, very applied engine studies, but we need to make this, fill in this gap in between these two areas. And again, we need to get information about the chemical mechanisms where we can provide input into the rate constants and everything that's necessary to use the chemical mechanisms. And the people in our engines group can use the output of the models. And what we feel is that by doing the modeling, typically what happens is when one develops one of these models and studies one of these models, one then does sensitivity analysis and uncertainty analysis to try and figure out what are the key reactions and the key steps in the reactions that are the most uncertain and leading to the most uncertainty in the output of the model. And then those kinds of considerations can feed back into our elementary studies and tell us which reactions are the most important to study. Similarly, the models can tell the engine guys, here's the parameters that you need to change, or here's the kind of fuel, how you change your fuel from one type of fuel to another type of fuel that might improve your output of emissions or whatever it is that your goal, your efficiency might be. So what we really see is that by introducing this modeling capability, that we'll be able to both use the feedback with the elementary aspects of the program as well as the very applied aspects of the program and make a much more unified whole. in the long run, what we want to do is then sort of expand this sort of net of feedback loops to include other aspects of the fuel development and the engine development, and use those to sort of improve sort of the overall big picture. So in one aspect, we can tie in with people developing biofuels and alternative fuels by using the modeling and engine studies to optimize the fuel and engine performance and to suggest new ideas for biofuels. And then the biologists or whatever can feed back to us and tell us, no, we can't make this particular fuel or this modification of the fuel, but rather we can provide you with something different, and then through that process, hopefully end up with an optimum fuel and engine sort of parameters. Similarly, by connecting all of this stuff with the people that are processing the biomass feedstock and the people either using bioprocess to transform that feedstock or using catalytic methods to transform the feedstock, again, by feeding back into this whole big picture that we hope to get optimized fuel and optimized engines that can use those fuels. And finally, this ties in with the idea of generating the feedstock. If we can give best ideas of what kind of biofuels or what kind of alternative fuels to generate, then we can tie in with those people to get new ideas. So ultimately, the idea is to develop an integrated team that for the development and optimization of advanced engines and fuels. We're starting out sort of in the fundamental aspect, but by increasing sort of the size of our scope, that we can hope to include these other areas and get an overall picture that leads to our goal. Thank you.